We're going to talk about highly reliable cloud-native DNS service. So please, I would like to know, raise your hand if you've ever experienced a DNS outage in your life. Okay. Yeah. I mean, the good sign is there is some awareness of how important DNS is. The bad thing is probably that we don't yet have it under control. But let's see what we can do about that. We will maybe need the slides on the screen. So, my name is Joel Studler. I'm here with An Hong Mai and Fabian Schulz. We are all DevOps engineers for Swisscom. Swisscom is Switzerland's biggest telco and IT solutions provider. The company is currently on the transformation from being a pure telco to becoming a tech company. We call that from telco to techco. That's a storyline that goes through the entire company. If you want to hear our CTIO talk about that, you can scan this QR. We will also share the slides later if you don't manage to scan all the QRs today. And a talk we've given earlier this day about evolving GitOps, or a version half a year ago back, given by myself and Ashan or at KubeCon. You can have a look at these resources. That this whole DNS story ties into this overall telco to techco story. So, but enough about Swisscom, let's talk about DNS. The title of the talk is DNS in 5G Core, or at least it contains the buzzword 5G Core. So the requirements, or there are some characteristics to DNS in 5G Core. So the first one is we only serve specific zones. It's private zones, it's privately hosted and only privately accessible. So it's within the 5G core, which also implies there will only be a moderate throughput from, we're talking about tens to hundreds of requests per second, not like hyperscaling DNS services with millions or, more requests per second. And the last characteristic is low latency. That might apply to other DNS services as well, but in the case of 5G Core, it's crucial because it will affect the overall service quality heavily. So that's why we need low latency. So that's the characteristics. Let's talk about the requirements. We have identified 6 different requirements. The first one is proximity to consumer. So we would like to have our DNS service be as close as possible to the DNS consumer, which is the 5G core. That means we cannot allow SaaS, so it needs to be on-prem. It should be fully automated, GitOps driven, so no manual interaction is allowed in this system. It should be geo-redundant HA, so we should build a system that spreads across multiple Kubernetes clusters and multiple availability zones or geo-regions. So we cannot have singletons. That's kind of an obvious one, I hope. We need advanced DNS features such as NAPTR. So we cannot just use CNAME and A records. NAPTR, in case you don't know it, it's kind of a regex substitution on DNS, similar to Nginx rewrite rules or something. You're used to in HTTP maybe, but that's used for phone calls in the 5G network. Then Kubernetes integration, that ties into the automation part. We really want to have a fully Kubernetes integrated system. The way to go currently is ExternalDNS, which is a tool from the Kubernetes project. So we don't allow create, update, delete actions outside of the Kube API. The reason for that is the 5G core is running on Kubernetes, so we want to integrate as much as possible into this Kubernetes layer. And the last thing, probably one of the more significant ones, is we want to reduce the amount of single points of failure. So we really want to distribute as much as possible. So this means we shouldn't allow a shared management system. We should have independent instances. So these are the requirements. Let's have a look at the architecture. So this is an architecture diagram of the service we've built. It's quite, it can look quite overwhelming. Please bear with us. So we're going to try to break it down for you bit by bit. So let's first halve it from a single dual cluster setup to a single cluster setup. And I'm going to start explaining to you the in-cluster DNS that is used in Kubernetes. So this Kubernetes DNS consists of a CoreDNS instance on the bottom right, which is the kube DNS in the kube system namespace. You can have an optional node cache, which that's documented in the Kubernetes documentation as well. That's actually caching the DNS records on the node level. You can have that, you cannot have that. It doesn't really affect the overall architecture, so we're not going to talk too much about that. It can help you increase stability, reduce latency, and all these things to really fine-tweak your DNS service. The way this in-cluster DNS works is usually a pod will ask for some service in some namespace. Eventually, this Kubernetes DNS will receive this request, and it will check in the Kubernetes API if there is a service by that name. If there's a service by that name, it will return a cluster IP, and the pod will be happily able to reach the IP behind that service. It's built on CoreDNS. CoreDNS is also a CNCF project, and it uses kubeAPI as a backend, so there's no state within the CoreDNS instance. So the feature, it's quite simple. It's in-cluster service discovery, so the pod will be able to reach the service through a name. What it doesn't feature is it doesn't expose anything outside to Kubernetes, so it's really only valid and usable within the cluster. And it doesn't support custom resource record creation, such as your Amex records or whatever else you need. There are some resources in the slide deck. I'm going to skip this. If you're interested, please have a look. But what this means in general is we need some kind of DNS server or service that can actually store our records. And we call this the authoritative server, which needs to store the actual records we want to create. So we've identified 3 different tools or technologies. First one is CoreDNS, which is a candidate because it's used in the Kubernetes DNS already. It's the same tech stack. Then we have PowerDNS, which is a heavily used open source DNS service or server, which is also deployed on-prem, and Route 53, also one of the more popular SaaS DNS services. So the comparison between the 3 leads to some favorites. I'm going to go through it. So external DNS support is given with all of them. We can create simple A and C name resource records with all of them. When we look at the NAPTR resource records, CoreDNS doesn't support it. We would need to change CoreDNS or the CoreDNS design or the plugin design at least. With PowerDNS and the Route 53 solution, it is supported after we implemented the fix. So we had to fix some logic in the Kubernetes external DNS project itself. So that's now also a check. And the proximity to consumer, obviously for the 2 on-prem solutions, this is given. So we have a clear winner, which is PowerDNS. That's why we decided to build this authoritative server with PowerDNS. So we've looked at the Kubernetes DNS. We're going to zoom out now, and Anne is going to show you a bit more about the orchestration around this authoritative DNS.
Yeah. So thanks, Joel. So we have just compared several solutions for the authoritative server. Let's now explore how we can automate its management. Let's now explore how we can automate its management with the external DNS. We choose externalDNS as it is a Kubernetes native application, and as you can see in our setup, in our architecture, external is deployed in a separate namespace with the authoritative server, and also all the resource records are defined as a Kubernetes custom resources of kind DNS endpoint. External DNS also excels at syncing any resource record to the backends. In our case, this is the PowerDNS server. This means that external DNS watches over several resources, such as service with load balancer IP, Istio Gateway, and DNS endpoint using Kube API. It then updates or creates the corresponding record in the server with the PowerDNS API. This ensures that all our records are in sync with the Kubernetes resources. For the creations, we make use of the external DNS annotations for the type A records, where the name is defined in the annotation and the IP address is fetched from the status field of a service or an ingress. Let's see how this works in the context of the state management. To ensure a reliable deployment environment, we store all manifests in Git as the one for the service kind here. And as I mentioned earlier, this is where we declare the DNS name in the external annotations. And once applied in the cluster, the external DNS will fetch the IP from the status and create a record in the backend as shown in the slide. It is important to note that with this setup, we eliminate the need of using static IP addresses in our configuration. This approach enhances scalability and reduces manual intervention, making our deployment pipeline more resilient and efficient. I'll hand over to Fabian for a demo on what I just described.
Thanks. So let's go to the next slide. Here you have a QR code where you can see all the resources I used for the demo. I'll show it again later. So with this, you can replicate the whole setup on your local machine and also run the demo. And we also have the slides there. So we'll start with a first simple demo. So here you can see at the top, I have a local kind cluster, and at the bottom, just my shell. I have a K9S running, just some terminal UI over kube control. And you can see, as before explained, we have the DNS namespace. In there, we have two deployments. We have the external DNS and the PowerDNS. So now let's add some services. So we'll go navigate to the demo 1, to the demo 1 folder. And in there, I have some service. So you can see here, we have a simple deployment, an Nginx deployment. And then we have a service. And here you can see the annotation that Anne just mentioned, where we define the host name. So the host name we use is nginx.5gc.3gppnetwork.org. And you can see it's of type load balancer. So let's apply this to the cluster, the service. So we apply it to the cluster. We can see the app coming up with the Nginx deployment. Now let's have a look at the services. So here I list the services, and we can now see here the Nginx service. We can see it got an external IP. So we have metlb running as load balancer. It assigned this IP. So now let's go back to the pod. So now we have external DNS. We'll look at the logs of external DNS, and we can see external DNS is syncing all the records constantly, and you can see it found this new service. It created the Nginx and called the PowerDNS API to add the entry there. So now let's quickly go to the GitHub. So here you can see the GitHub. There I have some notes, so I don't need to type everything. So you can see this is just what we did. So I added a service, external DNS saw it, and wrote it to the PowerDNS. Now let's ask for this record. Oh, this is the wrong window. Here, oh, I don't have. Let me go copy it again. Now let's go back. All right. So we have a DNS utils pod in the top. You can see I just call dig with the nginx.5gc request. And here we say where we want this request to go. So this you can see is 0.12. If we go back to the services, we can see that. So this is our here, the PowerDNS service 96.0.12. So we'll ask it. We do the request, and here you can see we get as this response the external IP of our Nginx service. So the one here. And of course, this also works for DNS endpoint CRs. So you can see I have a DNS endpoint CR. I can apply it again to the cluster. Here, let's have a look at the DNS endpoints. We can see this was just generated 3 seconds ago. Let's go back to the pods and look at the logs of external DNS. We can see here we have the create command from the endpoint 1, so it correctly found it. We can run this command again with endpoint 1 this time, and we get the expected response. So now I'll just quickly launch the script to prepare for demo 2, since there's going to be a second demo, and I'll hand it back.
Yep, thank you. So in addition to what Fabian just presented, I'd like to give you the final piece of our architecture. As you can see, there is no connection between the pod and our PowerDNS server, which is why we introduce another CoreDNS forwarder, as it is already used in the cluster, and so the deployment is quite straightforward. And then we make it as a default forwarder for all the built-in instances. From there, the new instance will forward queries for a specific domain. In our case, it's the 5GC domain, and to the PowerDNS, and the rest to the Swisscom server. Furthermore, as you can see, our new forwarder has a load balancer IP, which allows external consumer to do queries to our PowerDNS server, and so it can the consumer can communicate with the services or application inside the cluster. I'll hand over to Fabian again for another demo.
All right, let's go with the second demo. Let's have a look at our cluster again, what has been changed. We have a look at the pods at the top, and we can see there's a new CoreDNS deployment in the DNS namespace. Let's see how the configuration of this one is. So for that, we list the config maps. In the DNS namespace for the CoreDNS, we have the config map, which defines what this CoreDNS does. And if we scroll down, we can see here the policy. So we forward all requests for the 5GC domain to our 10.96.0.12, which is our PowerDNS service. So let me quickly go back to this page, so we see the image. All right, so now we checked this one. So we checked the CoreDNS and saw that the configuration forwards here. Now we have this one, so we want that this CoreDNS, I clicked on the window, forwards to our forwarder, which is on 0.11. So let's go back, and we can see that in the kube system, the CoreDNS, so we edited this one as well. And you can see here that the first forward is the Kubernetes internal, so the cluster local. So this you can see, this is the request here. So first it responds with the pod and services from the Kube API. And then if we continue scrolling, we can see that we have the default forwarder to our own CoreDNS instance, and then the backup to the node. All right, so to show this, now what we can do is, as before, we can use the same command. So we use the dig command, but now we can remove this the PowerDNS IP, because we can now just use the node local. So you can see I get the response. And of course, this also works if I use the Nginx. And I'll also remove this so we can see some more information. All right, so we can see here we have the correct response. Maybe let's have a look at the services here. So you can see this is the IP. And you can also see that the server that responded is the 0.10. So this is actually here you can see this is the kube DNS of the kube system. So the forwarding has worked, and we got the expected response. Now there's one more thing I want to demo. It's just this for an external consumer. So if an external consumer wants to consume our DNS service, they can call the load balance IP. Let me quickly navigate back and get the command. I don't need to type it. All right, so what do we do here? So here I'm running in a Colima, so this is just a VM, and I exec in the VM, and I just do in there the dig. So this is not inside the cluster, this is outside of the cluster. And here you can see I call the 1.0. So this is an external IP from our load balancer here. So this is our CoreDNS external service, which we defined. And when I do the request, I also get the expected response. All right, this is already the end of the second demo. There's going to be a third demo, continued. Now let's go back to the slides. Give this, thanks. All right, so now we've seen the single cluster deployment. Now let's extend it to 2 clusters. So we just duplicated what we had before. So here we have exactly the same at the bottom cluster. We have the top, the burn cluster, and the bottom, the Zurich cluster. You can see the bottom one has its own external DNS, its own PowerDNS. They're completely decoupled. Each one watches their own resources and puts them in their authoritative server. So now we want to use this setup of 2 clusters. So what we do is first we add a second external DNS at the top. You can see here there's a second external DNS instance which watches the resources of the burn cluster. And now instead of calling the API of its own authoritative server, it will call the API of the other authoritative server, which means that all the resources which are in the burn cluster are also represented in the authoritative server of the Zurich cluster. Of course, we want this also the other way around, so we add an external DNS instance in the Zurich cluster, which writes the updates up. All right, so what do we have now? Now we have an in-sync of 2 clusters. Both have the same entries. And they're in sync. But the cool thing is everything is independent. Like there's no connected database, no sharded, there's nothing. So this is really nice. So now we want to use this. So to use this, we need to add some fallback routes. So for example, if we have a look at the CoreDNS here at the top, if its own PowerDNS is not responding, we add a fallback route to the bottom one. So it will get the requests, we forward the request to this one. And of course, we want this to be the other way around. And now we'll add another fallback route in case our whole DNS namespace, something is wrong there. So here we can skip over it and just go to an external DNS. These are just 2 examples of fallback routes, of course. You could also imagine more of them. So now let's come to the next demo, so to the multi-cluster demo. First, we'll go here to the demo 3. Then we'll open another K9S window here, since now, of course, we have 2 clusters. So you can see at the top left, we have kind DNS 0, top right, we have kind DNS 1, so we have the 2 clusters. What has changed here? So in addition to the DNS 0, which has been generated 50 minutes ago, we also have now a new external DNS deployment, the external DNS 1. I'm listing the services here, but this is the same in the pods. So DNS 0 and the DNS 1, which has just been generated, you see 80 seconds ago. We can actually have a look at the logs of the new. And you can see here, if I look at the logs, so it found already all the resources and applied them and synced them to the PowerDNS of the kind DNS 1. So to show this, let me quickly grab some commands from here. So this now we need to start to look where we do the NS lookup. So you can see I select the context here. So now I select the context kind DNS1. So this is the right cluster. I again do an NS lookup. This time I use NS lookup. It doesn't matter. They go NS lookup, the Nginx, and we get the response. So this is from the service from the left cluster here. We have it in the right cluster. And of course, this also works for our endpoint we defined, endpoint 1. And we have the response. So now I just want to show you that, of course, this works in both ways. So I have another DNS endpoint CR here. You can see this is just endpoint 2. So we'll apply it. The DNS endpoint CR2. No, we want the DNS endpoint CR2. And we want to apply it to the cluster 1, which is the right cluster. So now we can have a look. Let's have a look if they got it. So we can have a look. You see, all right, endpoint 2, they created. So the external DNS 0 found it and is writing it into the PowerDNS of the left cluster. And the external DNS 1 also found it and is writing it in the right one. So now we can just do the NS lookup for endpoint 2. We can check kind cluster 1, we have it, and we can of course also show it in kind cluster 0, the left one, and we also have it there. So everything works as expected. So now let's see what this brings us by starting to break some things to see that then it's still working. For this, we'll start, so we simulate kind of a failure of the PowerDNS. For this, what I do, let me show the pods on the left screen here. What we do is we scale down the, no, this is the wrong command, sorry. I need to get the one to scale down, yep. So what we do is in cluster on the left one, kind DNS 0, we scale down the PowerDNS deployment to 0 replicas. You can see it disappeared. Now let's do the NS lookup in kind DNS 0, and we still get the response. So this is from the right. So this is from the DNS CR defined in the right cluster. We can also do it in cluster 0. We also get a response. You can see it. So what's actually happening is we are here, we do a request, the request gets forwarded, and then the fallback is activated, and this authoritative server is responding. Maybe you saw that there's now something red, and this is, of course, because the external DNS 0 tries to write it in its own PowerDNS, and if we look at the logs, we can see it cannot access it because it doesn't exist anymore. And another cool thing of having those independent deployments is that everything still works. So I have an endpoint CR3. Let's apply the DNS endpoint CR3 to kind cluster 0, so the one which is in a bit degraded state. We apply it there. We can see that the 0 is not working anymore, external DNS 0, but the 1 still caught it, so saw it and synced it to the kind DNS1 cluster. So now let's do the lookup for this new 3, endpoint 3, and we can see everything is still working. So this is really neat. So maybe we need to break some more things since it's still working. For that, we'll scale down the CoreDNS deployment in our DNS namespace. So the CoreDNS in the left cluster, we'll scale it down to 0 replicas. So this one is also gone. And now I can show you that this is a real demo and that if we do now, we don't get a response anymore. It doesn't matter for which one we ask. We don't get a response anymore. But as I said, we have a fallback route, for example, for if this doesn't work anymore. So if I do a NS lookup for google.com, we still get a response. So we still have a cluster which is kind of working, and we can try to fix it. And what is nice that now if I the PowerDNS deployment, I scale it back up. So let's say we fix it, this one comes back up. I'll quickly kill the external DNS so it restarts faster. So this is just going to restart. And the nice thing is I don't need to do anything. The external DNS is just going to start again. And as soon as it started, you see it started, and it will sync all the entries again. So the full PowerDNS was gone. There was no database, nothing in the backend, but everything is synced again. So this is the nice thing about using all those cloud native and Kubernetes with constant reconciliation. All right, so this was the demo. You can find all the resources here and also the slide. Then let's go back to the PowerPoint.
Yeah, thank you very much for showing that. It's very impressive. So we think it's a fairly stable and reliable and good solution. However, there for sure are limitations to it. So first limitation is that it's self-dependent. So we are producing the record or the DNS service on the same cluster where we consume it. That will lead to some self-dependence issues. You can easily mitigate that by just having your dedicated Kubernetes clusters for the DNS service. The second limitation is given by the design is we use Kubernetes resources only, so we don't allow any changes outside of the Kube API. That's something we think is good as well because we limit the pipeline of changes to GitOps or Kubernetes. The third limitation is given by external DNS. We think that external DNS is not suited for service discovery. I'm going to go into a bit more detail to explain that. So the first thing is it's interval-based synced. So external DNS syncs on a certain interval and will do bulk changes on the DNS backend. So we will have delayed resource record creation. Then there are no health checks integration, so the DNS record will be there regardless of the status of the app. So we cannot rely on the external DNS to check for app readiness. Then multi-cluster round robin. assume you have an app that spreads across 2 clusters, and you would like to create for each instance the same A record to have round-robin DNS. That doesn't work because the external DNS needs to own the resource record. And the last but not least thing, I think, that's a crucial design issue with external DNS. Assume you have a cluster that runs a few apps, and you also have external DNS. If that cluster goes completely offline, and even if you have redundancy, external DNS will not revoke the DNS entries. So you will need some tight monitoring and some additional automation to avoid this from being an issue. So these are the limitations. Let's have a look at what we achieved. So I'm going through the requirements again. Proximity to consumer, it's given by having an on-prem deployment. It's fully automated, GitOps driven with external DNS. It's geo-redundant and HA by using multiple clusters. Fabian has shown that we're using multiple clusters and we can spread them to wherever we want. So that's given. We fixed this NAPTR issue in external DNS, so we can now pretty much do any kind of resource record. Kubernetes integration with external DNS, that's given. We're fully Kubernetes resource-based. And the last thing, reduce the single points of failure. We've shown with the independent PowerDNS database backend and the cross-cluster syncing, we actually have a fully distributed control plane. So with that, I thank you very much. Thanks for being here. Please scan the QR, check it out, and enjoy the rest of the day.
Cool, thank you. We do have 3 minutes for questions, so I'll go through as quickly as possible through them. So was an NAPTR fix not possible for CoreDNS as you did it for PowerDNS and Route 53?
Yeah, so the fix is in external DNS, but CoreDNS, it's called KaiDNS, this plugin in CoreDNS. It does actually only support a very few records. So. CoreDNS is not supposed to be used for free-form DNS records. That's what they say. Yeah.
Okay. Is there any reason you are not using PowerDNS everywhere, as the forwarders and caches, for example?
Yeah. So I think we chose CoreDNS because it's the same tech stack as the Kubernetes DNS. It's this very same tool, so we don't need to build up know-how twice. And with PowerDNS, so PowerDNS has the recursor, I think it's called, and for forwarding, and that's a completely different product. So we didn't want to build up multiple know-how for multiple tools.
Yeah, fair enough. No, I apologize. Go back. Fat fingers. Oh, come on.
Scale up.
So it was that one. How do you debug monitor it, given it has so many components?
So we didn't cover that in the talk. We didn't have the time actually to do that, but we have we have the usual monitoring, Prometheus, Grafana, and so on. And we do have end-to-end tests using TestCube. So we run like end-to-end tests to test the chain if everything is still working. So that's our plan, and we're still expanding on that. And yeah.
Yep. Yeah. Quite a complex system. You need definitely need.
Definitely. Yeah.
That is, how do you do the failover HA of alt PowerDNS?
So we don't.
Fair enough.
No, it's independent systems, right? So the only thing that so that's something we didn't show. The external clients in a 2-cluster setup, they will have the 2 IPs of the CoreDNS instances, and therefore you are HA. Right?
Yeah. And final one. How do you scale the multi-clusters up? Does each cluster write to every other cluster, or is there a central interchange point like ESB? Yeah,
it's in a way like a full mesh between external DNS and PowerDNS instances. So we are in fact having a 3-node cluster, or a 3-cluster system, sorry. And this means 3 external DNS clients and 3 PowerDNS servers. So 3 external DNS instances for each cluster. So it's like this system just scaled to 3. Yeah.
Cool. Awesome. That's our time. If you have any more questions, I'm sure you're going to stay here for the drinks and after party. So do network. Thank you very much. Please, one last round of applause.
Thank you.